All right, so yesterday we did a little investigation on what the derivatives of sine and cosine are, and we basically just kind of used some estimation of secant slopes to estimate what the slope is at certain points of sine x, and then make a conclusion about what the derivative of sine x is and what the derivative of cos x is. Now, as I mentioned yesterday, these are not definitive proofs because they're kind of like we're using estimates of secant slopes. So the proof that we can use for sine x is using the Newton quotient. This is how we can prove all derivative rules. So just as a reminder, the Newton quotient, if I have the function f at x equals sine x, the Newton quotient tells us that f prime at x is equal to the limit as h approaches 0 of f at x plus h minus f at x all over h. So usually before we plug into this formula, I like to figure out what f at x plus h is, just so that I don't have to do it inside the Newton quotient and keep copying everything down. So here we have sine of x plus h. And if we think back to advanced functions, we actually have a way of expanding out the sine of x plus h. Can someone just grab that back door there? We actually have a way of expanding out the sine of x plus h, and it is not sine x plus sine h. How do we expand something like the sine of x plus h? Grayston? Okay, so we have to use the compound angle formulas, right? Kaylee?
Like sine x cos y plus cosine sine y?
Yes, so if we look, I gave you guys the trig identity sheet in this package. Let's look at the trig identities here. We have sine of x plus something, and it's going to expand out into sine x times the cos of the something, which in our case is h, plus cos x sine h. So that's what we're going to use to expand this out for our proof. So sine x cos h plus cos x sine h. Let's put this all into our Newton quotient now. Okay, and then we're just going to subtract f at x, which we know is sine x, all over h. So at first glance here, there's not like tons that we can do because usually we need to evaluate this limit at some point. I can't plug it in right now because we'll have division by 0, which we know is undefined. I also can't really common factor in h because they're inside the cosines and sines. So often if we don't know what to do, we will gather things that are common here. So if you notice, there's two terms that have something common. Yes, so these two have a sine x. So we're just going to kind of rearrange here. We're going to rearrange so that we have those two terms next to one another. And I'm also going to split these into their own fractions. So this one's going to be over h, and this one's going to be over h. So it's the limit of this entire thing. And there's a rule of limits that we've used in previous proofs that says if I have the limit of two expressions that are being added, I can actually take the limit of each individual expression. And I'm allowed to do that. So we can actually take the limit of both of these. I'm also going to just common factor the sine x from the top as I do that. Okay, and then there's one little extra thing that we need to do before we can actually evaluate here because we're still getting over zeros here, which is not helpful. And that is that we can actually remove the pieces of these limits that don't depend on h. Okay, this is the limit as h approaches 0. So anything that does not depend on h, I can actually just bring out front because I know that that piece will not be affected by the limit. So I'm going to do that for both of these. Okay, we're still running into a problem here. We still have over h's. So the only solution to this is really, if I graph these functions, we can observe what's happening to the actual graphs of the functions. So I do just so happen to have graphs of these functions right here. So this is the graph of the first part. This is the cos of h minus 1 over h. As this approaches 0, what is y approaching? Yep, so as we approach from the left and the right, so we're approaching x in this case, or it's like our h in our other formula. As we approach 0 from the left and from the right, y is approaching 0. So we can use that on here. We can just say that from observation of the graph, we know that this is equal to 0. And then for the other one, we're also going to observe this graph because we still have this issue of it's the sine of 0 over 0, so it's still indeterminate there. So taking a look at the other function. As we approach an x value of 0, we are approaching 1 on this function. So we can say by observation of the graph, oops, that's cosine, this limit is equal to 1. So of course this ends up being 0, and we're left with the cos of x. Okay, so this and this, we would say this is by observation of the graph. And this is the derivative. This is f prime at x. So we've just proven that the derivative of sine x is indeed cos x. So we can, if we needed a standalone proof of cosine, we can prove it similarly using the cosine addition formula. So you would have like the cos of x plus h, and you can kind of expand and do kind of a similar thing. I'm going to do kind of just like a secondary proof of cosine, which depends on this above proof here. So now that we've proven that the derivative of sine is in fact cosine, I'm going to use a little identity here. And if I want to figure out what the derivative of cosine is, I'm actually going to say that cosine is equal to the sine of pi minus x. And I'll show you where I got that from in a second. Okay, so if we scroll back up to the top here, looking at our transformation and cofunction identities, we see that cos of x is equal to the sine of pi minus x. So that's the identity that I'm using here. Okay, so we are expressing cosine in terms of sine because we've just proven the derivative for sine is cosine. So we're just going to use a little trig identity to help us to start this out. So when I go to find f prime at x here, what is the derivative of sine? It's cosine, we just proved it. So it's the cos of pi over 2 minus x. Now, the derivative of sine x is not the same as the derivative of sine with something inside here. So we have to do kind of like a little chain rule thing here. This is the derivative of the outside. What's the derivative of the inside? Negative 1, yeah. So this is the derivative. This is like outside prime. This is the derivative of the inside. Okay, so we're kind of doing like a chain rule thing here. And if you guys look back at your identity sheet, can you tell me what the cosine of pi over 2 minus x is? So if we look back at our identities, the cosine of pi over 2 minus x is actually equal to sine x. So we're going to switch that back into sine x form. That's right. So you have the negative here. And we know that cos of pi over 2 from our trig identities is equal to sine x. So Therefore, we've just proven, as a proof that follows the one above, this isn't a standalone proof, it needs to follow the one above because we've now proven the derivative of sine x above. We'll use the derivative of sine x to prove the derivative of cos x. Okay? If we have a standalone proof for cos x, it will be proven similar to how we proved the derivative of sine x with the Newton quotient above. But this one's a little bit quicker because we've already proven the derivative of sine x. Essay?
Before us to prove the derivative of cos x, can we prove sine x then use it to prove cos x?
Sure. All right, so as I mentioned in the proof above, the derivatives of all of these functions that we see in example 1 cannot possibly be the same, right? Even though they're all sine x, they all have different interiors, or if they have different exponents on them, we need to kind of gather our derivative rules that we've talked about in the past and apply them to these new functions here. So when we go to find the derivative of things like this, we are going to kind of do like a bit of a chain rule thing. And it's going to say, take the derivative of the whole thing. So what is the derivative of sine? It's cosine. And then you need to multiply by the derivative of whatever is inside the sine.
2.
So that's going to be multiplied by 2. So when we simplify this, it will be like 2 cos x of 2x. Okay, so it's kind of like chain rule. With these guys, if this confuses you, when we say sine squared x, we actually mean like sine x all squared. So if you feel like that's going to confuse you to see sine squared x, I would suggest that maybe you write them like sine x squared so that you can understand how we do the derivative rule here. So we're actually going to use chain rule here. We'll do derivative of the outside, so apply power rule, bring the 2 down, subtract 1 from the exponent. And then we need to multiply by the derivative of the inside, which is the derivative of sine x,
Cos.
which is cos x. Now, we're going to apply some identities in some cases in order to simplify expressions a little bit. So there actually is an identity for 2 sine x cos x. Does anyone remember what this identity is? Or if you look at your identity sheet, can you find it? It's the double angle identity, and this is equal to the sine of 2x. So we're going to use the double angle identity to simplify here. Great. Okay, this one's a little bit different than the one we just did because the one we just did was like the whole thing squared. This one is just the interior squared. So same idea, kind of like a chain rule thing. So derivative of sine is cosine. And then we need to multiply by the derivative of the inside. So what's the derivative of the function inside sine? 2x. So I'll have 2x times cos of x squared. Great.
Oh, this one goes.
Yep.
Question. For sublets, why are we saying dy over dx? The other ones we're saying y prime.
Yeah, so you can, as I mentioned yesterday, you guys can use those interchangeably. Dy over dx is sometimes a little bit better if you're actually evaluating after at a particular x value. Technically, it's just a little bit more proper. But yeah, if you want, you can use y prime. Anita?
I still understand why you don't do like cos 2x.
So I first have to take the derivative of this entire thing, which is cosine of the thing, right? Just like when we use chain rule here, the inside doesn't change yet, right? So I have to first apply power rule, and then I have to multiply by the derivative of the inside. So that's the same thing here. Okay, I'm just going to let this equal y so that when we do the derivative, we can use y prime. Any thoughts as to what we would do for this derivative? Michael, what do you think?
Well, so we, there's 2 sine pi, pi times x, so then you have, so so then 2 so then you would derive, so you derive sine, so you get 2 cos, and then that's the outside.
Okay, what derivative rule am I applying here? Let's just start with that.
Oh, I looked at the wrong question, never mind.
Okay. Kind of power rule, but there's a bigger rule that we need to go by here before we use power rule. Product rule. We have the product of 2 things. So we're going to do the derivative of the first times the second plus the first times the derivative of the second. And I don't think it's going to necessarily help us much, but we can common factor an x here. So we'll express it as 2 sine x plus x cos x. Oops. Okay, so product rule here. Any questions on any of those before we continue? So far, so good? Okay, so anytime you do derivatives of trig functions, you want to think like derivative of the outside times the inside. So if there's ever anything inside this trig function, you need to multiply by the derivative of that after you do the actual derivative of the function itself. Okay. Someone want to do the first one for us? Derivative of cos of 3x? Derek?
Negative sine 3x.
Good.
And then you times it by 3, or by 1.
Yep, you're right. Times it by 3. So you'll have negative 3 sine of 3x. So derivative of the whole thing, derivative of cosine is negative sine. The inside stays the same, and then we multiply by the derivative of the inside. Perfect. And again, you can use dy over dx, you can use y prime, whatever you want. Okay. Excuse me, I'm just losing my voice here. Michael, go ahead.
Okay, so you have 2 cos, pi, and then in brackets pi x.
Okay, so this is the constant multiple rule here. Hopefully my voice doesn't sound like this for the rest, but keep the 2. There we go, I'm getting it back. Keep the 2, do the derivative of sine, and then what's the last part, Michael?
You multiply it by pi.
Why pi?
Because it's the derivative of the inside.
Right.
No, I'm doing this, I'm looking up.
Okay, yeah, after you studied it.
After looking at it.
No, it's just get out of my notebook here.
This is why he brought his laptop so he could look smart.
I say. Yeah, so, oops, sorry. Constant multiple rule, leave the 2. Do the derivative of sine, which is cosine. Okay, so that's that part. And then we multiply by the derivative of the inside, which is pi. And then I'm just gathering up the 2 and the pi at the front. Is that good? Okay, my voice is almost back now. Okay, who wants to do the next one for us? Go, Grayston.
So I got sec squared x. 7 times x squared plus 3x times 2x plus 3.
Perfect. And just so we don't get confused as to whether this 2x plus 3 is inside the secant or not, we would usually write the 2x plus 3 at the front just so there's no confusion as to whether it's like the secant of just this or the secant of like the whole thing, right? So we just don't want any confusion there. So if you have a multiple, we would like to write that in the front wherever possible.
And what happened? See, I explained it quicker.
Not getting a lot of love today, Michael.
Michael never gets love.
8.
Any questions on that one? Pardon?
So, is it the same we've done, just with the
Yep. Yep, so if you guys remember, the derivative of tan from yesterday that we practiced with is secant squared. So we're just doing the same thing. Okay, so I want you guys to think of this as if it's like cos x all cubed. So we're going to kind of do the chain rule thing here. Does anyone want to try this one out?
Yes.
Essay?
Sorry, could we go back up?
Yep. Can I scroll, Essay? Okay, who wants to try this one out for us?
Or you can let him get
Okay, go ahead, Grayston.
So I did some
Shh. Yeah.
cos x squared,
Okay, so I'm just going to write cos squared x if we're good with that.
and then I times it by negative sine x.
Very nice. Okay, so I'm just going to put the negative in the front there. Yeah, perfect. So we'll have this. Any questions on that one? Essay?
Why doesn't Simon go?
Pardon?
Why doesn't Simon go to the front?
You can move it to the front if you want. Coefficients go first, and then if you want to rate it as sine x times cos squared x, that's fine as well. Doesn't really matter. Okay, next one. Let's think of this as 2 times sine x cubed minus 4 times cos x squared, like so. Okay, who wants to try the derivative of this one? Anita?
6 sine squared x
Perfect.
plus x minus 8 plus x times negative sine x.
Awesome. Okay, so power rule, subtract 1 from the exponent, that's how we get this, then multiply by the derivative of the inside. So same thing here, power rule, bring this down, multiply. Subtract 1 from the exponent, so we're left with exponent 1 here, and then derivative of the inside. Okay, let's clean this up a little bit. We've got a common 2 and a common cos x sine x. We're left with 3 sine x. Negative and negative makes positive here. And I think we can simplify this one step further. Does anyone see what we can do here? Yes, this is the double angle formula. So it's the sine of 2x. Maybe I will write that at the end, just so that it doesn't look like this is inside or multiplied inside the sine x. Okay, not a huge deal, but here we're using double angle identity.
The challenge question. Simple math.
Okay, are we all okay with that one? Any questions? Essay, you look confused. Can I clarify something?
I don't know how we got. So 2 sine x times 3 sine x.
like this row.
Yes.
So I'm common factoring a 2 from each thing here. And then I'm common factoring a sine x from each term here. And then I'm common factoring the cos x from each term. Does that make sense? Okay, perfect. Can I scroll here?
Yes, indeed.
Okay. What rule do we have to apply for this one? Product rule. So this is going to be our first. This will be our second. We're differentiating with respect to t. So oftentimes we'll say dy over dt. Derivative of the first. 3t squared times the second
One more time.
plus the first times the derivative of the second. Okay, we've got a common t squared here, so we can common factor that out. And I'm going to do, just gather those together there. So we'll be left with t sine t. Okay, next one, this is also going to be product rule. So we're going to do derivative of the first. Can someone tell us what the derivative of the first is?
I feel like it's cos of 4t times 4.
Right, so can we write 4 cos of 4t? Okay, derivative of the first, so the derivative of sine is cosine, then we multiply by the derivative of the inside, which is 4, times the second, plus the first, just as it is, times derivative of the second. So remember, we want to think of this as cos t squared. So what's the derivative of the second? So looking for the derivative of this here.
Oh, is it 2?
Cos t times negative sine, negative sine t.
Negative sine t. Good. Okay. If it's helpful for you, you can always write off to the side what the derivative of each are first before you start, and then just kind of plug them into your equation as you go if it's easier for you to think of it as like one and the other. Okay, I am going to clean this up a little bit. They both share a common 2. So this one has 4, this one has 2. I'm going to take a 2 out. Is there anything else common that they both share? They both have a cos t, so I'm going to take that out. And we'll see what we're left with here. Okay, not too much that we can do with this. This is kind of similar to like a compound angle formula here, like a cos minus a sine, but it has a 2 in front, so we can't apply the formula there. So this is really as far as we can go with it. Can I clarify any steps here for anyone? We're good? Can I scroll? Okay. So product rule again here. This is going to be our first. This is going to be our second. Does anyone want to try this one? Grayston, go ahead.
So the derivative of the first one, so it's just 1, so I'm not going to get it. 10 minus 10, 2x minus 1.
Mm-hmm.
And then it's plus x secant squared x, 2x minus 1 times 2.
Nice. So we'll just clean it up a little bit here. Put the 2 in front, so it'll be 2x secant squared of 2x minus 1. Not too much that we can do with that trig identity wise, so we'll just leave it there. Okay, so we're applying product rule here, and then we have to do kind of like a chain rule thing when we do the derivative of the second there. So outside and inside. Can I clarify anything here for anyone?
Probably not much.
Okay, the challenge question, this is just for fun if you want to like really challenge yourself. The derivative of this is insane, so it's not part of the lesson, but if you want to try it out, you can. The solution is, or not the full solution, but the final answer is posted for you in the lesson solutions. So if you want to try it out, you can. It is very hard, but yeah, it's a fun one.
Is this kind of thing be on the test? Like this
No, but if you could do this one, you can do any trig derivative question. So,
I will.
yeah, so you can try it out if you want.